Hello and welcome to the 741 channel. Thank you for stopping by. Today on the bench we have this Pyramid PS-36KX power supply. So I originally was going to make a video documenting the repairs that I made to this power supply, but it gave me so much trouble that I ended up just kind of stopping the recording of the video partway through and focusing on getting it repaired. So what I think I'll do now is go back through the process and walk through some of the things I did, some of the things that gave me some trouble, and some of the things that I learned along the way. So hopefully you'll find this type of video helpful or entertaining, and if you're not familiar with this sort of thing, maybe you'll learn something from my pain, or maybe you'll see something here that I missed or should have checked in the first place. And if you do, feel free to leave me a comment down below and let me know. Anyway, let's get started by taking a closer look at the power supply. So here's a closer look at the power supply. First of all, you can see it's got two meters. It's got an ammeter and a voltmeter. Now, neither one of these is working correctly at the moment. We'll address that later. You can see that it's just got the standard positive and negative sort of screw type banana jacks here. It's got variable voltage on the front here. I'm not sure what the range is. I think it's a variable between maybe 12 and 15 volts or something like that. It's got a protection circuit built in so that if there is a problem with the power supply, this LED will flash and there's a piezo buzzer inside that will sound to let you know that there's an issue. And we'll talk more about that as we get further on in the video as well. And of course it's got a regular lighted on-off rocker switch here. So here's a look inside the power supply. Now I'll mention at this point that I don't have the cover for it. The owner who dropped it off here for me to look at kept the cover. So anyhow, what we have here is the main transformer, and from the specs this thing is good for 36 amps, at least at some amount of duty cycle. I wouldn't run it at that continuously, but it's beefy enough to supply some current. Here you can see we have the back of the meter faces, and you may be able to tell we've got some Christmas lights in here. Now those obviously aren't factory. That's a modification that the owner has made at some point in the past. And I've since disabled them. I'm not sure they were working anyway. And I'll talk more about those later on in the video also. This here is the main circuit board of the unit. Down here we have the standard LM723 regulator chip. There's a tip 41 transistor here, an SCR, and then a logic device that controls the protection and warning circuit over here. Back here we have a bank of newly replaced filter capacitors. I'll talk a little bit more about those as we get further along as well. Over here we have a cooling fan. Now this cooling fan is currently disconnected, as you may be able to tell, and the reason it's disconnected is because the bearings in this fan are all but shot. And then back here we have the main heatsink with the 4 TO3 style power transistors mounted to it. So the reason this power supply is here is because it wasn't working. The guy that owns this is a friend of mine, and he asked me if I'd take a look at it. He told me that one day it just stopped working and the protection circuit came on and was beeping. And when he put a radio on it, it wouldn't power the radio anymore. Here's a little bit of footage of what the power supply was doing when it first arrived on my bench. And as you can see, I've got my meter here. And I actually have the power supply hooked up to a load. I've actually got an old CB radio up here on the shelf that's out of the shot right now. You guys can't see it. But anyway, what we're going to do is we're going to just test this power supply now and see what happens. So the first thing I'm going to do is turn it on. And you can hear the protection circuit is active. Obviously, you can also probably see the light, or the LED rather, blinking on and off. So the power supply is indicating that it has an issue. So however, when I look over here at the meter, I can see that it's putting out 15 volts. So in its unloaded condition, it is putting out some voltage. Now if I turn the adjustment knob here on the front, you can see in the meter that nothing happens. And then when I try and load down the supply by turning on the CB radio, which is up here, you can see that it goes down to 2.7 volts. Let me shut this off so you guys don't go deaf. So after my initial assessment of the power supply, I noticed that the bank of capacitors back here was in pretty rough shape. Here's an example of one of them here. You can see they were all burst at the top and leaking and not in good shape anymore. So I knew these were going to have to be replaced. Now, along with that, and based on some experience that I've had with similar power supplies, I figured we'd have to end up replacing the transistors that are back here. Now, the transistors that were in this particular unit were these ST branded 2N3772s. So I let the owner know what I was going to do, and he offered to supply me the parts. So he ended up purchasing the parts, both these Nichicon capacitors and these new Motorola branded 2N3772s from eBay. Now, we'll talk a little bit more about that coming up. But anyway, once he dropped off the parts, I got to work replacing them. I put the new filter capacitors in, as you may be able to see here, and then I took the heatsink off and replaced all 4 transistors. Now, at this point, I'll cut over to a few clips of some footage from when I was doing that work. So with the screws removed, there's enough slack in the wires here to be able to tip this heatsink out and turn it 90 degrees just so we have enough access to get at the solder connection. So before I unsolder all these wires, I'm going to label them so I know where they go. I think what I'll just try and do is put some pieces of tape on here, 1, 2, 3, 4, so on and so forth, so that I can put them back in the right sequence later. So as you can see, I've got all of the yellow and blue wires unsoldered. I've left the red ones soldered to these tabs here. There's just a little bit too much metal there for me to heat up with my soldering iron, so I thought it would be easier to just leave those soldered and just undo the screws. So you can see I've got the first bracket out, and I just wanted to make mention that there's a little plastic insulator that the screw goes through and that separates the bracket from the heatsink. You want to make sure at this point that these little insulators don't get lost, and also that they're in good shape and not cracked or anything like that. If they happen to be cracked, they could be causing a short, which is causing your problem. So you can see here I've got sort of a mess of wires and my old digital multimeter here. This is a manual ranging digital multimeter, and I've got it set up to test the first transistor that I've pulled out of the power supply. Now, if you want to see more of an in-depth explanation about how I test these transistors, you can find a link to another video that I made in the description below that explains a little bit more detail about how I test these things. So anyhow, what I have set up here is I have the transistor's emitter tied to the negative lead of my multimeter. I've got the collector tied to the positive lead, and then I've got this loose wire here that is also tied to the connector. And when I put it on the base pin, so basically I'm shorting the collector to the base, if the transistor were good, we would see here in the meter, I don't know if you guys can see it or not because of the glare, we would see the infinite resistance that's being measured now go down to something measurable. But because this transistor is bad, it's not turning on. Basically, the whole point of this exercise is to use the voltage that the digital multimeter is putting out to turn the transistor on and get it to conduct and show a resistance measurement. But because that's not happening, the transistor is bad. So the first thing that we're going to do is clean this old dielectric grease off of the heatsink here. I've squirted a little isopropyl alcohol on there, and I'm just going to wipe it off with a rag. That stuff that's on there is pretty dry and crusty after all those years of being on there, and it probably wasn't doing much for heat transfer anymore, which could be part of the reason why these transistors finally crapped out. The next thing that I'm going to do is remove this mica insulator that's on each of the old transistors. You may be able to see it in the camera there. It's got some dielectric grease dried up on its surface that mates to the heatsink there, so we'll clean that off as well. Now, you can see that this is on here pretty tight. It's probably a combination of the dielectric grease kind of being dried up to it and the pin having some solder and stuff like that on it. So I'm going to just cut these pins. You want to be careful that you don't crease this because it can kind of break easily. But since we're not going to use these transistors for anything anymore, I'm just going to cut these blobbed leads off. And now we'll just kind of gently work that off. And there it is. You can see the insulator there. So I'll gently clean each one of these before we reuse them. The first thing that I'm going to do as part of the reassembly process is I'm going to put some new dielectric grease on the surface of the heatsink. That should be good enough for here. I've got a nice even but thin layer all around the surface of where that transistor will be. So next up, what I'll do is I'll take a transistor and do the same thing. I'll coat the body of the transistor with this stuff. So next up, I'll take one of the mica insulators here and drop this back onto the transistor, and that'll kind of seat down and sort of stick to the dielectric grease to keep it in place. The next thing that I'll do is I'll measure out and cut some lengths of heat shrink tube to go over these leads to take the place of those little insulator pieces that were on there originally. So I've got my heat shrink pieces cut, and you can see that I've got some of the lead still kind of exposed here because we're going to need to solder that later. So we don't want the heat shrink to be the whole length of the lead. In fact, I could probably trim these a little bit shorter and we'd be okay. The point is to just insulate the pin as it goes through the body of the heatsink so there's no chance that it can touch the metal. Next up, what we'll do is drop the transistor into the heatsink, and we'll make sure that we have the pins sort of lined up the right way. You can see that they are offset one to one side of the case a little bit there, and we'll match that up to what's on the heatsink and drop it in place. So you can see I've got that sitting on there. Now I probably have a little bit more dielectric compound on there than I really need, so we'll keep that in mind for the next ones. But anyway, what I'll do now is keep my finger on this and then flip it over, and we'll put in the first screw. So next up, what I'm going to do is I'm going to put in one of the two screws that holds the transistor in place. Now if you remember from disassembly, we've got that shorting bar that's still on the power supply back here. In fact, I think you guys can still see it in the shot. So we've got that there to deal with. So I'm going to put just one of the screws in place. So you can see the hardware here that I had set aside from when we disassembled it. There's a nut, a little washer, and you can see there's sort of this plastic shoulder insulator. So here's a look at the shoulder insulator now. Hopefully this is focused enough for you guys to see it. You can see that this little shoulder here is what sits down in the heatsink and prevents the screw from shorting to the heatsink, which in turn would short the case of the transistor to the heatsink. We don't want that to happen. Now, when I took mine apart, some of these shoulders either cracked or disappeared altogether, so all I have now is a straight washer. So we're going to need to deal with that eventually, but what I'm going to do for the purposes of this first transistor is use one of the shoulder washers that came out intact. Now, I imagine that these things get brittle with age, so if you're working on an old power supply, just keep an eye on it and make sure they didn't crack like mine did. And if they do, you'll have to deal with that. So what I'll do now is drop the screw into the hole through the transistor body, and then we'll flip it over. I'll make sure I hold my finger on the transistor so it doesn't fall off. And then on the other side, we'll now take the shoulder washer and we'll kind of gently put that on here and get it so that the shoulder goes down in the hole in the heatsink and provides that clearance and insulation that we need to prevent the screw from shorting to the heatsink. Now keep in mind you want to be a little bit gentle with this, especially if your power supply is old, because again, we don't want that to crack. So next up, I'll put the little split washer on, and then I'll just thread this nut on. For the time being, I'm going to leave this just finger tight. We don't need to crank this down, and even when we do tighten this up for the final amount, again, we don't want to tighten it too much because we don't want to crack those insulators. So now I'll pretty much repeat the process for the remaining 3 transistors. So I've come upon one of my insulators that lost its shoulder, as I was talking about in the previous clip. So let me show you what I've done to kind of correct that. Hopefully you can see on this screw here that I've got a piece of Kapton tape kind of wrapped around the screw a couple of times. Now the height of that is about 3/8 of an inch, and between the thickness of the transistor body, the heatsink, and the remaining part of the insulator, that should be just enough to allow the nut and washer to kind of go on here and not really contact the tape, but still has enough insulation there to prevent any shorting. So I'll drop this screw in so you can see what I'm talking about. Hopefully you can see there in the camera that there's a little bit of tape still protruding through the heatsink. So you can see I've got the insulator on there. Now of course, keep in mind you don't want to wrap too many layers of tape around or the insulator won't be able to slide over it. In my case, it was just a little bit too snug, but I was able to get it on there. And as you can see, I've got it all snugged up now, and it should be good to go. In fact, the screw behind it also has the Kapton tape, but you wouldn't be able to tell. As you can see, I've got all 4 transistors mounted to the heatsink. So we're going to flip this over and take a look. You can see that on the left 2, I've already prepared the screws and insulators for the shorting bar that we're going to attach next. So now we're going to go ahead and bring the shorting bar over and drop it onto the screws, and then we'll just reinstall the washer, the split washers, and then we'll put nuts on each of the screws, and we should be good to go for this side. And then I'll just put the nuts on each of these screws and snug them up. We should be good for this side, and then we'll repeat the process over on this side. So as you can see, I've got the heatsink assembly here ready to go. I've got it propped up on an Altoids tin right now to get it a little closer, because these wires are just a little on the short side, so we need this kind of as close as we can get it. I've got the soldering iron over here warming up, and I've also got all my little pieces of shrink tubing prepared. These are about 3/8 inch or so in length. So before I solder each of the legs, I'm going to drop one of these on each lead and get it ready to go and in place. Here's a little closer look at the heatsink just for reference. You can see this wire with the shorting bar is already all set. And then over here I've got the transistor leads with that little piece of heat shrink tubing in here. I think what I'm going to do to start off with is pre-tin the transistor lead. Then what I'll do is I'll freshen the solder that's on the end of the wire here. So before I start soldering, I just want to make sure that I keep my sequence here with my numbered pieces of tape. So we should be able to just solder this up and it should work good. So I've got the first one soldered. I'll just take a quick look here and make sure the solder joint looks good, and then we'll move on with the rest. As you can see, I've got all of the wires soldered back to the transistors, and I removed all my little pieces of tape. Okay, one thing I almost forgot here is we got to get this heat shrink tubing kind of shrunk around the transistor lead here so it kind of stays in place. So I'm going to use my hot air rework wand here, and I'm just going to use this flat-headed screwdriver. Hopefully you guys can see that. That'll hold the little piece of shrink tubing down, and I'll use this to kind of blow the hot air in place, and that'll get it kind of shrunk up around the transistor lead. Okay, so I think we're good to go on the shrink tube now. So I think we're all set with the transistors now. I got the heatsink screwed back on. But before I power this up and test it, I think what I'm going to do is address these leaky capacitors here. So let's get this board out of the power supply. It looks like it's just held on with 2 screws back here that go through standoffs to the main body of the power supply. So we'll get that lifted up so we can access the bottom of the board. So you can see I've got the power supply tipped over on its side so that I have the board sort of horizontal. And this way here I won't have to remove all those wires. I can just focus on the capacitors. So I'm going to start with the first one. I've put a little flux on here already, and I've turned up my soldering iron as high as it'll go to about 900 degrees here. And I've also got my solder sucker here. This has been heating up for a while. Now we've got a lot of metal on this board and a lot of solder to deal with, so I'm going to use the soldering iron to kind of get things flowing, and then I'll use the solder sucker to try and remove the solder. I think there's just a little bit too much solder on these to use the solder wick. That should be most of the solder on the first capacitor. Now, in fact, I can even feel here it's pretty loose. So now I should be able to just use the soldering iron here to kind of help wiggle it out the rest of the way. And there you have it. One thing I want to mention here is that the board conveniently has the positive and negative sides of each capacitor marked, so we don't have to pay strict attention to how these things come out, since we'll kind of know based on the way the board is marked. But if you're doing something like this on a similar power supply and your board isn't marked, make sure you pay attention to the polarity before you pull these things out. So now I'll just repeat the process on the rest of the capacitors here and remove all these bad ones. As you can see, I've got all of the capacitors out of the board. Now normally at this point I'd probably spend some time with some solder wick and clean up the solder on here, but I don't think I'm going to do that. All the holes on here are clear and should accept the capacitor leads. This board isn't the best made board in the world. I don't want to risk putting too much heat on here and lifting any of that copper, so I'm just going to leave it as it is. I think it'll be okay. I'm going to clean the flux off with some alcohol, and then this side of the board where the capacitors were sort of leaking, I'm going to clean that up as well, and then we'll put the new ones in. Here's a quick look at the old and new capacitors side by side. You can see the old one's pretty well shot, but you can also see that it's bigger than the new one. Of course, they are the same rating, 4700 microfarad at 25 volt, although the new cap is rated at 105 degrees C. I don't know if you guys can read it there or not, whereas the old one is only 85 degrees C, so that should help. Now, if these are really Nichicon branded caps and not some Chinese facsimile, they ought to be good anyway, so we'll just see what happens over time, I guess. So I'm going to start by inserting the first cap. I'm going to work my way from the back to the front. So anyway, I want to be mindful of the polarity, like I mentioned before. The side with the stripe on it here is the negative side, so I'm going to turn that around and match that up to the negative side of the board. I don't know if you guys can see it or not, but there is, I think I showed this before anyway, there's a negative etched into the side where the negatives go and a positive etched into that side. So we have an easy way to tell which way these caps should go. Okay, so what I'm going to do, I've got the cap in, I'm just going to bend the leads over so it stays in place. And now we should be able to solder that first one in. So I've put a little flux on there just to help things flow a little easier, so let's see what we can do here. Okay, so we should be good. The first one is soldered in. I'm just going to snip the leads and we'll do the rest of them here. So I think we're in good shape here. I've got all the capacitors soldered back in place. They should be oriented correctly. And I've even got these two wires here reattached where they need to go. So all I need to do now is screw the board back into place and we'll fire up the supply and see if it works. Okay, I've got the unit plugged in. I've got the meter over here. Oh boy. Let's try this again. So I've got the power supply plugged in. I got the meter hooked up and ready to go. Let's fire it up and see if any smoke comes out. Whoa. And it sounds like we still have a problem. Okay, I'm going to run this briefly. Now you can see that even though we're in protection mode, there is voltage on the meter, and the variable voltage control on the front of the unit seems to work now. It didn't work before. So, we're moving in the right direction. I don't know why the protection circuit is on though, so we'll have to dig into this a little deeper. So initially, after replacing the capacitors and the transistors, the power supply did power up and appear to work properly, with the exception of the protection circuit being on. So after about 5 minutes, the power supply stopped working again, or at least supplying power. The protection circuit stayed on, and I couldn't figure out why initially. And then I did another check on the new transistors, these transistors, and found that they were shorted. So I knew I had another problem here. So at that point, I dug out the schematic and I started probing the circuit board, looking for issues. So here's a look at the schematic that I used for this power supply. Now this is not the exact schematic for this power supply, but it's pretty close, and it's really all I could find that was close to this, so this is what I worked with. Now the way that it works is that normally the SCR is open. It doesn't conduct any electricity. And we have this circuit here, which consists of a Zener diode and a couple of resistors. So in theory, what's supposed to happen is that if the voltage goes above the 16 volt breakover voltage of this Zener diode, current will start to flow through this part of the circuit and cause a voltage drop across this resistor, R14. Now, once there's a voltage present at this point, it triggers the SCR, turning it on, and thereby causing a direct short right here and shunting all the current through this sort of direct short to ground and away from your equipment on the output of the power supply. Now, in theory, what should happen when this shorts is that the main fuse that's back here on the primary of the transformer should blow. And you can see here that it's a 6 amp rated fuse, at least for this schematic. So even though this fuse hadn't blown, I figured that maybe my problem lay here, that this SCR had been triggered, and my theory was that if that was the case, then there should be a voltage across R14. So that was the first thing that I probed. And so now I'll cut to some footage showing that. So I've been looking over the power supply a little bit here. So the first thing that I checked was the SCR. Now I believe this is working okay, but I don't believe that that is the problem. So let's do a voltage check on that first. I've got my meter set to DC volts. I'm going to turn this on. What I'm going to do is I'm going to probe across R14, which is right here next to the SCR. The top of R14 should be the positive side, and the bottom should actually be the ground rail. So let's take a look, and you can see that across R14 I don't have any voltage. That should mean there's no current flowing through it either, which in turn means that the SCR shouldn't be triggered. To check one more thing in this area, I'm going to measure the voltage between the cathode of Z1 and the ground rail down here. Now we should already know, because we're getting voltage at the output terminals, that this should be the same, but I'll just double check it in the circuit just to make sure. And as you can see here, we're getting about 15 volts, which is what I'm getting at the output terminals between the cathode of Z1 and the ground rail. So I think we're good there. So at that point I ruled out the SCR as a problem. After that, I went online and did some digging and found a voltage matrix for the IC723 chip. So at that point, I started comparing that voltage matrix to the voltages that I was measuring on this power supply, knowing that my pass transistors were shorted and still in the circuit. Now, I was getting some readings that were different than the voltage matrix, but they were still sort of in line. They were all maybe a couple of volts higher than what I was seeing on the voltage matrix. So I wasn't sure if that was attributable to the fact that I had a problem with the pass transistors or a problem with the 723 regulator. So now I'll cut over to some footage showing the voltage measurements on the 723. So now that it seems like the SCR is working, the next thing that I want to check is the main voltage regulator chip, the LM723. So I found a voltage matrix from an Astron power supply, which should be similar to this. Now, we could be going down the wrong path because they're not the same, but it's the only thing I have to go on at the moment since there's no voltages on the schematic that I have. Anyway, the setup that I have now is I've got the negative lead of the meter connected to the ground rail of the power supply. And I'm going to probe each pin and check its voltage. So I'm going to turn this on. It's going to start beeping again. Hopefully it doesn't get too annoying for you guys. But I'm going to probe each pin and see what we get for voltage. So as you can see, pin 1 is measuring 0, and according to my matrix, that's what it should be. Pin 2 is reading 16 volts instead of 13.4. Pin 3 is at 15 instead of 13.8. Pin 4 is 7.5 instead of 7. Pin 5 is 7.16 instead of 7, so that one's pretty close. Pin 6 is 7.15 instead of 7. Pin 7 is 0, and that's what it should be. Pin 8 is measuring 0 volts, which is what it should be. Pin 9 is measuring 13.9 instead of 8.7. Pin 10 is at 19.76 instead of 14.9. Pin 11 is 32 instead of 27. Pin 12 is at 32 instead of 27.2. Pin 13 is 15.16 instead of 16.3. And pin 14 is 0 as it should be. So as you saw, we have some discrepancies here. So what I think the next thing that I'm going to do is change out the LM723. We may just have a bad chip here. So I've got a new one. I'll unsolder this one and put the new one in.
That's the problem here, the windering snow and ice, right under the snow is now freezing it now.
So as you can see here, I've got the chip removed from the board. Now this one was soldered in. From what I understand, Astron power supplies use a socketed IC, and if I had a 14-pin socket, I'd drop one in here just so that in the future, if this ever needs to be changed, it will be a lot easier. But I don't have a socket, so we're just going to take the new chip that I have and put it in there. But this is a look at the old one. Now, I don't see any visible signs of damage with this, but that doesn't mean that it's good or bad. So I have a new one, we'll put it in and see what happens. So here's a look at the new 723 IC. I'm going to drop this in the board here and solder it back in place. I've got the chip in. I'm just going to put a little flux on here to help everything. Okay, so here's a look at the board where I've soldered the chip in. You can see all the leads are now connected. This maybe won't meet IPC soldering specifications. So then I ordered up some new transistors from Mouser, which I knew would be reputable parts. And this time, instead of using 2N3772s, I opted for 2N5885Gs. Now, the reason I did that was partly because the 2885s can sink more current than the 772s, but also because these were in stock at Mouser and the others weren't. But anyway, I ended up replacing all the transistors again with the new parts, and then at that point is when I turned on the power supply and it started working. So all that backstory brings us up to where we're at now. The power supply is on, the protection circuit and warning circuit is off, and we have a proper voltage here as measured by my fluke meter. Now, as I mentioned earlier in the video, these meters don't work. You can see this voltage meter is registering a voltage, but if I use the variable control here and change the voltage, you can see that the meter is not doing anything. And I can tell you that even though we're not drawing any current, the amp meter doesn't work. And of course, as I mentioned before, the fan is also not working at this point. So there's some things I want to address. So a few final thoughts before I end the video. Now, I never really did get to the bottom of what was wrong with this power supply. I have two kind of equally plausible theories, and maybe both of them are true, and maybe neither of them are true, but I suspect that what we were dealing with were some bad transistors that were sourced from eBay and therefore China. Now, these are stamped Motorola 2N3772. Now, we all know the dubious quality of Chinese products, especially those sold on eBay, and there's no telling how much Chinesium is in here versus real material. So I'm just suspecting that these just were really no good in the first place. Now, my other theory is that the voltage regulator, the LM723, was shot, and that when I replaced the transistors, the Chinese ones, they were okay, but because the regulator was bad, it self-destructed these within a matter of a few minutes. Either way, now that I've got parts sourced from Mouser in the unit, I can rely on those parts and know that for the most part they should be the right parts, and as you can see, it is working now. So in addition to taking care of the items that I mentioned, the backlighting, the fan, and the meters, I need to do some load testing on this and make sure that when I start drawing a fair amount of current on it, the power supply will keep working. But I'm fairly certain that it will at this point, and if it doesn't, I'll cover that in another video. So anyway, if you enjoyed this video or found it helpful, please give it a thumbs up. And if you'd like to leave a comment or subscribe, feel free to do that as well. And if you'd like to support my channel in another way, please consider visiting my Amazon store, which you will find a link to down in the description below. Thanks for watching.